Okay. So let's come back and take a look at the adjoining sums of squares and cross products model. Now, way back when so as we talked about the fact that it's going to be a family of numbers, just as we had before. And I talked in previous lecture about the fact that whenever you're looking at an adjoined sums of squares and cross products matrix, you'll have a column of ones. And you can identify that because what's going to be down there is the number 1. The average of a column of ones across all people is the number 1. And the nice thing about that is, in the off diagonal here and here, you'll see that you have the means of the two variables. So looking at this little matrix, I know that the mean of child height is 6.68 and the mean of parent height is 68.3. Now, to make a connection with classes that you've had before, in your training, you've seen two formulas for a variance. And we're going to use an adjoined sums of squares and cross products matrix to talk about variances and covariances, but also the intercept or the mean level. And, you know, because I'm older than you, I'm older than teaching evaluations. When I was going to college, about my second year is when people started to have teaching evaluations. It was very controversial. I always signed mine, and the teachers kind of liked that. But also back in those days, there were no computers. When you did an analysis, you did it by hand. Generally speaking, with large pieces of paper. And what we had were two formulas. One was called the definitional formula for a variance. And I see I have a mistake here. This should have a square on it. I'll make a note. X minus the mean squared divided by n is the definition of a sample variance. But the other thing that we had was something called the computational formula. And that involved calculating the square of all the numbers and adding those up and dividing by n, minus, well, the sum of x, adding up all the x's and dividing by n. Well, this number here is simply a formula for the mean. So when we were doing things by hand, we would have x, and then we would, next to that, you know, on a piece of paper, write x squared, and we'd write all of that down. And then we'd get a calculator. The calculators did exist, and we'd add all the squares together, and we'd add all the x's together, and divide by n, and take the sum of the x squareds divided by n minus the mean squared. Okay. So in terms of a path diagram,
I have a question for the formula.
Mm-hmm.
Can you just go up? So here, is that a line on top of the second x?
This one, yes. That's our notation for saying.
So for the second part, the second squared, is that a line on top of?
Line, no. In other words, this, if I add all of my x scores up and divide by n, that's the average. That's the mean.
Oh, okay.
So I could just as easily have written x bar there.
Okay.
All right.
Thank you.
So this, sum of x squared divided by n, well, that's this number. And the mean is this number. So what we're going to do is to draw an equation, a path diagram, that will express this equation. So I like to start small. So this is the path diagram that will do the work starting from an average sum of squares and cross products matrix that will get me, I think I'll make this a little bigger for us all, that will get me to the desired statistic I want to have down here, the variance of parent. So this is, we're going to play the same path diagram rule with the adjoined sums of squares cross products matrix as we did for a single predictor model with the deviation score matrix. It's just that what plays the role of the predictor is the column of ones, is number one, and what plays the criterion is the average sums of squares of parent height. And now I'm going to take these same trips as I had before to calculate the variance of parent from the data. Well, as we just did in our little rehearsal, which was kind of fun, what does this diagram say about the average sums of squares of the column of ones? Well, it's going to end up being the number one, this number one here. And what does this diagram say about the mean of parent? Well, it's going to be the number one times this number. So therefore, I know that parent height, that coefficient, is going to be 68.3028. Right? So it's exactly the same rules as before, except now in my diagram, I'm using the tracing rules to understand the average sums of squares and cross products and the means instead of just the variances and covariances. Now comes the last part. What does this diagram say about the average sums of squares of parent height? Well, just as before, one thing I can have is this coefficient plus the mean of parent times the number one times the mean of parent. Well, that's this thing. So I can arrange this if I want to solve for what this coefficient is. That's going to be the variance of parent is equal to the average sums of squares and cross products of parent minus the mean of parent squared. And that's going to give you this formula. That's the formula. So we know, because this is the computational formula for the variance, that this number down here in my path diagram corresponds to a variance. So sometimes people will talk about the standardized moment. This is just me trying to build a connection to other things that you've had in other classes. Sometimes we calculate the mean divided by the variance of x, and it's got a relationship to something called the coefficient of variation. Well, that involves this path diagram. And, you know, the coefficient of variation figures more prominently in things like biology, where they're looking at growth parameters and trying to look at how much variation there is, say, in the length of a tadpole. But, you know, this little diagram, you can look at it and we can still play the same games as we had before. What does this diagram say about the sums of squares of parent height? Well, it's going to be A times 1 times A plus A times the mean times the number 1 times the mean times A. And that's going to be the average sums of squares of parent height. What does this diagram say about the variance of parent height? Well, that's going to be A times 1 times A. And, you know, as I've said, you can read this a little bit like a Russian novel. You know, if this is the name of somebody you don't know, you can probably omit that little example. But what is perhaps more informative is to look at the path diagram for a single predictor regression model with a column of ones. Well, what does this model say about the variance of parent height? Let's start out with the column of ones. This thing, I use the letter O. That might not be a good one. That's going to turn out to be the number 1. The column of ones is going to have a sling value of 1. What does this diagram say about the mean of parent height? Well, it's going to be the number 1 times m. Therefore, this coefficient will be the mean of parent height. What does this diagram say about the average sums of squares of parent height? Well, that's going to be P, just as in the littler diagram, P plus M times O times M. Therefore, this thing will be the variance of parent height. Oh, now what are we going to do? Well, let's say, what does this diagram say about the mean of child height? Well, 1 times I is one way to get from here to here. Another way to get from here to here is to go 1 times M times B. And those two things together are the mean of child height. If you go back to your old statistics books and you look up the formula for what an intercept is, you'll find it's exactly that equation. You just solve for the intercept. Well, what does this diagram now? The ugly part is, what does this diagram say about the average sums of squares of child height? Well, that's going to involve a lot of things. The laziest thing to do is to come back and say E plus B times P times B. That's one thing I can do. I can say B times M times O times M times B. And that's all of the paths starting out with the letter B. I can also go B times M times O times I. That's legitimate. So let's do everything starting with B to rehearse again. B times P times B plus B times M times O times M times B plus B times M times O. And that's everything that starts on your trip out with this arrow. Well, we've done this one, and we've done starting out this path. Now let's turn to this one. I times O times I. That's okay. And I can go I times O times M times B. And that's it. So if you're playing around with this, for example, it would not be possible to say I times O times M times O, because I would have gone forward and then I can't go backward anymore. Now, one of the things I know from teaching this now in my 31st year is that, I tend to say, okay, this is how we do it, B plus B, M, O, M, B, and so forth. I tend to talk really fast because I kind of have this learned after 30 some odd years. But the thing that people ask about is, yes, indeed, you do go B times M times O times I, plus you do also do I times O times M times B. So you end up 2 timesing the path involving this part of the circuit. Now, usually at this point, people are going, oh my gosh, the other shoe has dropped. This is the part of the class where I lost it. So it's not the case that you've lost it. The computer is going to do the work for you on this. There's a couple of things you should look at, though, is that so long as I have arrows pointing from the column of ones to all my manifest variables, what sits down here is the solution in the variance covariance matrix. So just so long as I've got this triangle pointing all my manifest variables, I can kind of ignore it and come back down here and say, this diagram says that the variance of parent height is P, the covariance of parentist child is PB, and the variance of child height is E plus B times P times B. That little diagram is really all you need to worry about. Alma, okay?
I have a question. So can we follow a path like that, B and then P and then M and then O and then I?
No, because if I do B and P, I've grabbed a sling, and after grabbing the sling, I can't go backward.
Okay.
So what I would tell you to do is, you don't have class on Monday, so of course, spend the day wishing you were in class, maybe not getting up at 8, but look at this part of the presentation, and it matches you up with what the numbers are. And what I've said before is what's on this part. All right. And, I talk a little bit about the software and so forth here for you. I wrote down the number 2, and I didn't write down what equation I need to fix. So hold on just a second. 3.24. All right. That way I can correct it. And I mentioned to some people before they came in, but I got a whole bunch of notes from Amazon that the books are in delivery, and they say that they should arrive tomorrow. So if you don't get it tomorrow, let me know. All right. Are there questions?
Yeah, I have a question. So is the 1 the variance of the constant, but the variance of constant should be 0? Why is it?
I'm sorry. I was just noticing that. That was a bad letter for me to choose. That's the letter O.
But you said it's 1, right?
Yes, it's the number 1, right. Because yes?
But what I learned is that the variance of a constant should be 0.
Right. So when we're looking at a sling there, that sling is not a number that represents a variance. It represents the average sums of squares.
Okay.
So, and that's an important point that it's good that you raised, that we'll remember that this number is not a variance, and this number is not a variance.
Mm-hmm.
This is the average sums of squares. So it's every child height squared and then added up across all the child heights. And the same fashion, this number 1 is the number 1 added up across n people and divided by n.
Okay, thank you.
Okay. So in our diagrams, when we're using that, this becomes the number 1. And because, in this diagram, this parent height variable is still a statement about the average sums of squares of parent height. It always involves this mean squared term, though. But what I was trying to say before is, if you have a diagram and you have a column of 1s present in it, and you point at all your manifest variables, what happens down here is actually a statement about the variances and covariances. So it's sometimes helpful to come back in. There we go. So here's our little Onyx data set again. If we were to play around with that inside of this computer, I can add the constant. And I can write, so notice what happens when I don't add the constant here. And I'm saying, I want to have explicit means. In other words, every number's in there. This number down here is 393 and 757. That's the average sums of squares. So when I want to make a variance, all of a sudden now that number becomes this sling now becomes a variance. In the same fashion over here, I can free this parameter and this number becomes a variance. And I can free this parameter. And now I have a path diagram that shows me, that calculates for me the variance covariance matrix downstairs.
So I have a question. Why? What does free parameter mean? What we are doing with freeing the parameter?
It means that in order to describe this system, I need to have a number associated with an arrow or a sling. And if I have a fixed parameter, that means regardless of the data, this is going to be the number 1. So, what we're doing here in this diagram is we're using the average sums of squares and cross products matrix, but we want the diagram to calculate something we're interested in, namely the variances and the covariance. Okay, so this is kind of the fun thing for me, is that let's now draw a picture that will do something even more interesting in our model. Namely, I don't really like variances, it's a little secret. I really think standard deviations make a lot more sense because it's the average squared deviation, square root of it. So let me delete this, and this, and this, and this, and this. And let me now draw in a latent variable. Well, this latent variable, I'm going to fix it to the number 1. And now I want to have this be a free parameter. And I want to free this parameter. Well, what does this diagram say about, no, it's for some odd reason, I need to send the data to the model. I'm going to do the same thing over here. I want to fix this to the number 1. And I want to free this. And I want to free this parameter. Okay, so let me move this around a little bit, make it bigger so we can see it more. So now we're telling a slightly different story. What does this model say about the mean of the whisk score? Well, excuse me, I'll have to get into why it gave me a negative number there. Okay. So what does this diagram say about the mean of the first whisk score? Well, it's the number 1 times this number. And what does this diagram say about the mean of time 2? Well, it's the number 1 times this number. Well, you can look at what I told you before. As long as I'm talking about arrows pointed at all my manifest variables, what's up here turns out to be variances and covariances. Well, what does this model say about the variance of whisk 1? It's 6.36 times the number 1 times 6.36. That is, this becomes the standard deviation of the variable. And the same thing occurs for whisk time 2. The standard deviation is 7.24. Well, what's the definition of a correlation coefficient? Well, it's the covariance between two z-scored variables. The correlation between the two variables is 0.81, which is what we had before. So now I've drawn a diagram that sort of looks like, I don't know, maybe a dog or a cat, that has as it's giving me statistics that I find more useful, the means of the variables, the standard deviations, and the correlation between the two of them. And this highlights the fact that there's more than one structural equation diagram you can draw. It doesn't make one any worse or any better than the other. It just is a diagram that gives me the statistics that I am interested in.
So the meaning of these manifest these scales, for example, can change. Sometimes it can give us mean, sometimes it can give us different things based on the path that we follow.
Yes, based on the diagram you draw, yes.
Can you explain again how the 6.36 is the standard deviation? I think I kind of understand that.
So let's just come over here and look at, maybe it helps if I just kill this and we just talk about this little piece. So what does this diagram say about the mean of time 1? Well, as we talked about before, that's the number 1 times this. So this is the mean. What does this diagram say about the average sums of squares of whisk time 1? Well, that's going to be 18.78 times 1 times 18.78 plus some number times 1 times some number. And as we talked about before, if this is the mean, this part of my model has to be talking about the variance. Well, one way to do that would be to have a latent variable that has a free variance and a fixed path. Let's do that just for the hell of it. Let's fix that parameter and let's fix it to the number 1. And then come up here and free this parameter. Oh, my goodness. Now, this is exactly what was in the book before. The average sums of squares of whisk time 1 is 1878 times 1 times 1878 plus 1 times 40.46 times 1. Well, this thing then is the variance. If I want to take the square root of that, I'm going to come in and fix this to the number 1. Then I'll come downstairs here and I'll free it. And that now gives me the average sums of squares is 1878 squared plus 636 times 1 times 636, which is going to give me some number like 40. So my teaching strategy is I'm going to do teeny tiny little diagrams to illustrate how an adjoined sums of squares and cross products matrix works and how variance covariance matrices work. And these are connected. So if you're doing behavior genetics, for example, behavior genetics runs off of the idea that there's a latent variable out there and it's got a variance of 1. And that explains a variance component. And what they do is they draw these little diagrams, and these paths are doing the work of calculating standard deviations. It looks like a latent variable and factor analysis, but it's different because there's no error variance down here on this manifest variable. Okay. I can come back and we can mess around with that some more. Come back into here. I did want to say, I hope you all got it, but I made a brief introduction to the AMOS graphical user system because some of you folks like SPSS. And actually, AMOS is kind of nice because it looks prettier than Onyx. It's a commercially available bit of software. And it has enough options in it that you can make publication-ready path diagrams for your stuff. So, I mean, you can watch me on YouTube, like and share me on YouTube, but if you want, we can come in and talk about that in class if you find it interesting. And the chapter kind of ends with exactly what I did in class of you can make standardized versions and so forth and so on.
Would you say that AMOS is as robust as M+? So if we wanted to do something for publication, I just don't read AMOS as much as I read M+ in methodologies, and so I don't know, at least in my area of developmental.
Yeah, AMOS is pretty easy. And the other nice thing about AMOS is it also has some foolproofing in it. If you try to draw a diagram that isn't right, AMOS will tell you, are you sure you want to do that? Like you have a manifest variable, there's no error term on it. Are you positive that's what you should do? And the other nice thing about AMOS is you can read in SPSS and Excel files and I believe even SAS.sav files. So, you can port things in from a variety of things. If you want, I'm happy to fire up AMOS and mess around with it in class. The other thing that you can play with is M+. M+ has us write everything out line by line. Come to think, all right. And so if you're doing a regression in M+, you'll notice that we have a little model statement in here. And we say y on x. And if I want to give that parameter a name, I put it in parentheses afterward. And the y variable is a free parameter. That's what that little star means. And I can give it a name. And the parent variance has a star on it. I can give that a name. Intercepts are denoted by hard brackets. They're also free parameters, as is parent. And that's what the code looks like for M+. Well, one of the nice things about, again, Onyx is I can do a regression in Onyx. I need to add a variance here. And I can say, oh, I've got a diagram here. And then I can right click on that and I can say show a script. And this will then show me, it'll write out the program for me. So all I need to do, if I want to run this in M+, is to reference my raw data and copy and paste this into M+ and run. Another thing I can do, I mean, if you have other platforms that you like, is some people like Lavon because it's free and it's on R. And I speak Lavon too. And this is the R code for running a regression in Lavon. It generates it automatically. So all you need to do is talk about how you would draw the diagram, and Onyx can write the program for you. And that might save you some time at the beginning when you don't know exactly how to write the syntax. Generally speaking, Fox's SEM package isn't used very much. Just to scare you a little bit, if you like OpenMX, it will also write the OpenMX code for you. This is what that looks like. You have to specify everything in matrix form. Not something anybody in this class right now is going to do unless you're going to go into behavior genetics, where thinking about your data in matrix form is kind of nice. it also has a line, OpenMX has a line-by-line mode, which is, you know, every little equation, just like we saw in M+, but as you can see, it's ugly. You have to say if it's a free parameter or a fixed parameter and so forth. It's a bit of work. So in terms of what people in this class have done, yeah, I kind of like Onyx, and I can either copy this and run it in Amos and make the same diagram, or I can automatically generate my M+ or Lavon code this way and cut and paste it into there, and that gets me up to speed quickly. And you know, I did the same thing for this, and if you want, there's other data examples we can play with. In terms of where we are, I think, you know, the material that I did in here is exactly what we had before. There's two little examples I'd like you to think about here. And it's in service of the question that really the path diagram, there's nothing magical about it. There is an assumption of causality, if by causality you mean I'm pointing at something, saying, but if I have a deviation score matrix, if I'm looking at a variance covariance matrix, maybe I'm interested in what the variance of A plus B is. I might have, say, a time 1 and a time 2 score. Well, maybe in my data, all I have is A and B, and I don't have the sum scores. Well, inside of a structural equation model, you can write the following diagram. And all this is saying is the sum variable is equal to 1 times whatever A is, plus 1 times whatever B is. That's an equation form for what adding two numbers together is. Well, I can now look at this and say, well, what's going to happen? What is the variance of my sum variable going to be, even though I don't have it in my data set? Well, it's going to be 1 times the variance of A times 1 plus 1 times the covariance of A and B times 1 plus 1 times the variance of B times 1 plus 1 times the covariance of A and B times 1. That is this formula right down here. And so that helps us understand in our head what things make the variance of a sum big or small. Well, if all of the things being equal, if the variance of A and B are kind of whatever numbers they are, if I have a zero covariance, if they're uncorrelated, then the variance of the sum is just going to be the variance of A plus the variance of B. If these things are, if the covariance here is some positive number, the variance of the sum is going to be bigger than that. Similarly, if the covariance between A and B is a negative number, the variance of the sum is going to be less than the sum of the variance of A and B. And that's kind of, you know, okay, I can draw a diagram. This helps me maybe understand if you talk about Cronbach and Furby is one of the golden citations in psychology on difference scores, sum scores. Well, I can also look at the variance of a difference score. Well, that's saying A minus B is the latent variable of my difference score. Well, that's going to be 1 times the variance of A times 1. Negative 1 times the variance of B times negative 1, that's going to be the variance of B, plus minus 1 times the covariance times 1, plus 1 times the covariance times minus 1. That's going to be minus 2 times that. So again, if the variance of the sum, I'm sorry, if the covariance between A and B is 0, the variance of the difference, I should have written in difference here. It's my day to find mistakes. is going to be simply the sum of A and B. And if this is a positive number, the variance of the difference is going to be the variance of A and B minus 2 times that. And similarly, if this is a negative relationship between A and B, this is going to be a negative number times a negative, that's going to be a positive. And those are just, again, small little diagrams that calculate a statistic that you know about. Maybe you don't have it in your data. In my life, I've used this in educational data sets where people will report GRE verbal and GRE quant, but they don't report GRE total. Well, I don't actually need to have the data. I can calculate a variable that will represent the sum, and I can just point arrows out of that variable to make the statistics that I want. So we're at time. I do, in keeping with, let's talk about really small things, I'd like you to start reading 3 variable models. And what's happened in the past is we'll talk about 2 predictor models. Probably we'll get through this, and then I'll talk about statistical significance of path coefficients and how the statistical significance of regression and analysis of variance models is just a tiny, tiny bit different than the statistical significance in structural equation modeling. But we'll talk about that on Wednesday. And the goal of this part is let's talk about little structural equation models with only 3 variables dancing around. I cheat toward the end, I talk about a 4 variable example, but that'll give us some practice in the tracing rules and what does this diagram say. All right, we're at time. I have office hours if you want to chat. Other than that, I shall see you on Wednesday because Monday is a holiday. I will be on the internet Monday if you have questions. Like many of you have sent me the homework thing already, but if you run into bumps over the weekend, let me know. You can email me over the weekend too, but I'll also be on the internet on Monday, okay?
Sounds good. Thank you very much.
All right.
Have a good weekend.
I have a question. Can I share my screen and then show off what I did on X?
Sure. Should I stop the recording? Yeah, let's